session on superconductivity, and our first speakers are Maria Zarafakis and Sandy Lavito from CSU Stanislaus, and the title of their talk is Improvement of Physical Properties in High TC Superconductors with Lead Doping.
So good afternoon, my name is Maria Zarafakis.
And my name is Sandy Lavito.
And we are undergraduate students from California State University Stanislaus, and we are here presenting a portion of a much larger research project on improvement of the physical properties of high temperature superconductors utilizing lead doping. And the main superconducting material that our research focused on is bismuth, strontium, calcium copper oxide 2223 with lead doping, also known as VISCO 2223. Our lead doping ranges varied from 0, so no lead doping, to about 0.6 lead doping. And the picture shows one of our VISCO samples. So how did we prepare these samples? These samples, VISCO 2223 samples, were prepared using the solid state reaction method, which is basically a process of heating and annealing, which is shown in this diagram. So essentially, the samples are placed inside a crucible and ground, and then they are heated to various temperatures and allowed to anneal for 2 to 20 days. And then they are slow cooled, and then they are reground once more.
So the first question that we had to ask ourselves with our VISCO samples was, is lead doping really all that necessary? So in order to answer this question, we created samples with no lead doping. As you can see on this graph of magnetization versus temperature in Kelvin, the plots vary here, but they actually reach more or less the same TC onset. What this means to us is that no matter how much we change the properties we could change in the lab, those being the temperatures at which we could heat them to, and the amount of time we allow them to anneal, we really couldn't push undoped VISCO 2223 much further than this low onset of 80 Kelvin. But what this graph also shows is changing the temperature and the annealing time does seem to have an effect. And so from this graph, we can see that sample D, right here, is the best sample in that it has a high TC onset, it has a steep curve, and it has a relatively stable tail. So those are the three properties we are going to be looking at in all of these graphs. And as you can see up here, the difference between sample D and all of the other samples is that it was heated to 860 degrees Celsius, and it was allowed to anneal for 103 hours and utilized 3 grindings. So now that we were able to answer that first question, so we knew we did have to dope it, now the question remained just how much lead should we use? So we created samples ranging from 0 to 0.6. So basically 0 or 30% lead dope. What we noticed with 0 and 0.1 is that the trend tends to be very similar. But it's at 0.2 where we start to see this low TC onset coexisting with the high TC onset. So this seems to indicate that the more lead we add, the higher the TC onset seems to become. But now the question was, how much is too much? So we went on and did 0.3, 0.4, up to 0.6, and we discovered that the plot for 0.3, being this one right here, has a very stable tail, a steep curve, very high TC onset. So the rest of our experiments concentrated on samples that utilized a 15% lead doping range. Oh, yeah, so all of these samples all have 15% or 0.3 lead doping. The only difference, again, is the temperature at which they were heated and the amount of time they were allowed to anneal. And so this graph is also magnetization of each sample versus the time Kelvin, temperature Kelvin, my apologies. And of these samples, sample E, as we can see, is the best one because of a relatively stable tail. It has the steepest curve, and high TC onset. And the difference of those samples is that sample E was allowed to heat up to 860 degrees Celsius and had 119 hours worth of annealing. As you can see, the other ones range from 800 degrees Celsius all the way to 860. So 860 was sort of confirmed to be the temperature at which we wanted it. What's interesting to note on this graph is sample E, which was the best in the previous round, is actually not the worst. In this sample, 0.3G, being this one right here, actually has the most stable tail, the steepest curve, and the highest TC onset. So we now know that sample G is the best one. And why is that? Sample G here has 860 degrees Celsius as well as the previous one did. But if you notice, the time we allow to anneal is much greater. Now when we compare sample G with the rest of the samples, it continues to be the best. But what is interesting about this graph is that sample 03J actually has the greatest TC onset. However, if you notice, it starts to have that low phase as well. All of the samples had the low phase, but also had the high phase. And for practical applications, we're concentrating on superconducting materials that have the majority of this high phase. So despite its really high TC onset, overall, sample 03G is actually the best. And the difference between G and J, the temperature is the same, but the annealing time is vastly different. G has it at around 180 hours. Sample J has it as a whopping 580 or above. And now that we believed that we had the sample we really liked, so G, we wanted to see if we could recreate it. So we created another sample called L under similar conditions. And as you can see on this graph, the plots more or less confirm that this is a proper recipe. And we can compare the temperatures and the annealing times, and they're within acceptable ranges. While we concentrated mostly on trying to get the highest TC onset, that alone would not give us the best recipe, or would not confirm that we have the best recipe for a practical superconductor.
So the next major physical property of superconductors that we needed to focus on was something called the magnetic critical current density. Now, when you increase the magnetic critical current density, you increase the amount of current that you can flow through, say, a wire that's made out of a superconducting material. So the greater the magnetic critical current density, the greater the practical uses of the superconductor will be. So one way to get the measurement of the magnetic critical current density is through the measurement of the hysteresis loop. And how you get this hysteresis loop measurement is you apply a magnetic field to the superconducting material, and then you gradually take the magnetic field away from the superconductor, and it creates this loop that you see here. Now, this is lead doping ranges from no lead doping to 0.3 lead doping. And as you can see, the 0.3 sample actually has the largest width. Therefore, the width of the hysteresis loop is actually proportional to the magnetic critical current density. So the larger the width, the larger the magnetic critical current density is going to be. So we can predict from this graph that the 0.3 lead dope sample will have the largest magnetic critical current density. And when you compare 0.3 again to the other lead dope samples, sample ranges from 0.4 through 0.6, again, 0.3 has the largest width. So we predict that it would have the largest magnetic critical current density. So we plotted the magnetic critical current density in amps per centimeter squared versus the various lead doping ranges at two different temperatures. And as you can see, the 0.3 lead dope range for both temperatures has the largest magnetic critical current density.
So in summation, the purpose of our section in this larger project was to find the best preparation recipe for VISCO 2223. And we realized that as long as we doped our VISCO 2223 with less than 30% lead, it's remained a superconductor. Anything more than that, the material was no longer a superconductor. During our research, we discovered two transition temperatures. One, a low TC phase at 80 K, and a high TC phase at 110 Kelvin. All samples showed having both, but again, because we're concentrating on practical applications, we wanted samples that had the majority of the high TC phase. We found the highest transition temperature to be 115 Kelvin at 15% lead doping and using extended annealing.
For the actually has about 4 million amps per centimeter squared, while a non-lead dope sample has about 1 million amps per centimeter squared. So doping the sample with 0.3 lead actually increased magnetic radial current density by about 4 times, which is a very significant increase.
All right, and that would be the conclusion of our presentation. Thank you very much.
Do you happen to know what like the current best modern high TC material, like what's the highest possible transition temperature so far?
I think it was 128 Kelvin,
But the issue is with, depending on the superconducting material, some of them are under pressure, some of them without pressure. So it depends on the application you would be using it for. That's how you determine what is the best for your particular situation.
Well, I guess I was asking from a naive perspective of what's the absolute highest temperature?
We are trying to figure that out.
Okay.
But that's an excellent question. Thank you very much.
Other questions?
Thank you for your time.